Dear experts, teachers, and students, it's my great honor to attend the 2021 EAI International Conference on Communications and Networking in China. My name is An Li, and I come from Hohai University. The topic of my report today is Cloud Edge Collaboration-Based Data Mining for Power Distribution Networks. My report includes the following 5 parts. First, the research background. Second, the problem analysis. Third, the proposed algorithm. Fourth, the experimental verification. And fifth, the conclusions and references. First, the research background. China's electricity consumption has reached 7.2255 trillion kilowatts in 2019, an increase of 4.5% over the same period last year. The limited data storage and real-time processing capacity of cloud centers have restrained the evolution of power distribution network. Because the user-side data cannot be fully explored to build more elaborate power distribution network at present. Then, with a large number of devices widely connected to the power distribution network, there are higher requirements for data acquisition and analysis of power distribution network terminals. By 2019, there were more than 50,000 dedicated cloud computing units for power management deployed in China. However, about 50% of the 10 kilowatt power distribution IoT equipment was still blindly adjusted. This indicates that the small-size users' data collected by power equipment was either missing or not efficiently explored yet. The power distribution IoT contains both static and dynamic data. The static data comprises the various attributes of the equipment and the topology data for the static networks. The dynamic data are obtained from the voltage monitoring system and the power system monitoring networks. The real-time operations of the power distribution IoT are monitored through the terminals, and the resulting real-time status data are stored. The power distribution IoT environmental data include information collected from the switchboards, such as the temperature, humidity, and water level. It also includes data obtained from monitoring the external operating environment of the power distribution IoT equipment, such as the access control and the small animal detection data and the equipment status, to allow for efficient transmission and timely understanding of the internal environment in the switchboard. By means of the power distribution IoT load and the environmental data processing, we can effectively prevent the occurrence of accidents, avoid operation environmental misjudgment, improve the safety protection of equipment, and reduce excessive costs. The wide access of the power distribution IoT terminal equipment results in collected data that power distribution terminals is a crucial resource for designing power demand strategies. The diverse information can be analyzed to facilitate dispatch planning, resource allocation, alarm reporting, and the provision for support services. We propose mining the value of data that originate from PD IoT tasks in terms of the execution delay, computing complexity, and power consumption as shown in Figure 1. If a task should be executed with a short execution delay and has low computing complexity and power consumption, is considered as a sensitive task that can be promptly carried out at the edge layer. Otherwise, if it has a long execution delay and high computing complexity and power consumption, it is considered as a non-sensitive task that can be carried out at the cloud layer. In DCP algorithm, we define data of terminal task set D, then calculate the execution delay, complexity, and power consumption of each task. The weighted values of these three parameters are obtained. If the value is greater than the upper limit of the given threshold, it is transmitted to the cloud. If the value is between the upper and lower limits of a given threshold, it is transmitted to the edge. If the value is lower than the given threshold, it is discarded and not processed. Case 1. The delay, complexity, and power consumption of the text data are mined, and the weighted sum is carried out. If the value of the weighting function is greater than the upper limit of the given threshold, it indicates that the storage and the computing resources used to process the text data are large enough for multi-objective measurement. The system of power distribution network then transmits the text data of the terminal to the cloud server for processing. Case 2. The delay, complexity, and power consumption of the text data are mined, and the weighted sum is carried out. If the value of the weighted function is less than the lower limit of the given threshold, it indicates that the contribution value of the text data to the power distribution network approaches zero or none after the text data is analyzed and processed after multi-objective measurement. Therefore, the system of power distribution network will consider whether it is a data error. Moreover, it is also necessary to avoid waste of storage and computing resources. In power distribution network, the system will not process and abandon this text data. Case 3. The delay, complexity, and the power consumption of the text data are mined, and the weighted sum is carried out. If the value of the weighted function is between the upper limit and the lower limit of the given threshold, it indicates that the storage and the computing resources used to process the text data are small after multi-objective measurement. The system of power distribution network then transmits the text data of the terminal to the edge server for processing. Case 4. After the text data is input into the system of power distribution network, if the text data is special, such as a large venue event, should have direct communication channels with the cloud server, and the venue uploads the future activities arrangement to the cloud server. The cloud server will arrange the power supply plan after accurately predicting its daily load and guarantee the venue is going smoothly. Fourth, the proposed data processing based on DCP algorithms are verified by experiments. The experimental platform and the data set used are as follows. In the power distribution Internet of Things, the greater the complexity of the service data, the greater its readiness, and the more difficult it is for the services data to be restored. As can be seen from Figure 3, the complexity of electrical fault survives is within a stable range, and its maximum value is 0.4709. The minimum is 0.4533. After many interactive numbers, the average value is 0.4709. 0.4654, belongs to between 0 and 0.5. Therefore, electric fault data complexity is considered to be easy. If delay and power consumption is not considered, its worth suggested, and the electric fault is preferably transferred to the edge. Figure 4 illustrates the average execution delay for electric faults. We compared the three cases of the traditional cloud computing architecture, the cloud-side cooperation algorithm based on decentralized cloud, and the proposed task allocation scheme. As shown in Figure 4, TCC has the largest average execution delay of 81093 nanoseconds. The average execution delay of DE is 51038 nanoseconds, which is approximately 37% smaller than that of TCC. The proposed task allocation scheme has the smallest average execution delay of 280.25 nanoseconds. Compared with TCC, the reduction is approximately 65%. This is because the proposed DCP scheme can reduce the data redundancy for the tasks and avoid the waste of computing resources. Figure 5 illustrates the average power consumption for electrical faults. As shown in Figure 5, TCC has the largest average power consumptions of 30.17 milliwatt every hour. The average power consumption of DE is 19.11 milliwatt every hour, which is a reduction of 37%. The reduced power consumption can be attributed to the multiple edge computing units DE, which can take the calculation and storage pressure of the cloud. The proposed task allocation scheme has the smallest average power consumption of 10.57 milliwatts every hour. Compared with TCC, the reduction is approximately 65%. This is because the proposed DCP scheme can reduce the data redundancy for the tasks and avoid the waste of computing resources. Figure 6 illustrates the total execution delay and the power consumption for up to 560 tasks in N, for which the three schemes are also compared. As shown in Figure 6, when the number of processing tasks exceeds approximately 450, the execution delay in DE and the proposed scheme are sharply increased. This is because the computing and the storage resources of edge services are limited and insufficient to support multi-task processing synchronously, which can lead to the cloning informant. In contrast, the much more abundant computing and storage resources in the cloud compared to the edge result in a linear increase in TCC. Fifth, conclusions and references. We first describe the Cloud Edge Collaboration System model and analyzed the terminal data type, which include load data and the environmental monitoring data. Then, for users' data, a data processing algorithm of DCP is proposed to effectively reduce the data redundancy for the tasks and avoid the waste of computing resources, and improve the quality of Cloud Edge collaboration service. Experimental results show that, compared with TCC, the proposed DCP can save about 65% of execution time and power consumption. Data privacy protection is the standard to judge the reliability of a system. How to effectively protect terminal data privacy under the promise of ensure the correlation of attributes is the next research goal. Thank you for listening.